So this video is going to discuss the simulation of a first order transfer function. So we have our transfer function, and this particular transfer function we have is 1 divided by s plus 5. So remember that if you let s go to 0, that gives you the steady state value. So the steady state value of this to a step response is going to be 1/5, right, or 0.2 units. Okay, so if we have our system h of s and we're going to feed this a step response, a unit step response, and we want this we want to find x of s, right? So to do that, right, so the transfer function is basically saying the output divided by the input, that's equal to h of s, which is 1 over s plus 5. So what we're going to do here is cross multiply, and so I'll get x of s plus 5x of s is equal to my forcing function f of s. And so then if I go and solve or change it to the time domain, right? So remember, change the time domain, and s means the derivative. So this is d x of t dt plus 5x of t is equal to our forcing function in the time domain. And so our change, our derivative function then, is dx of t divided by dt is equal to minus 5x of t plus the forcing function. So we want to simulate this using Euler's method. I'm going to simulate this in the Octave software. So here's my Octave software, and so I'm going to create a new file. I'll call it tf.m. And so the first thing you always want to do is clear it out. I'm also going to clear the display, and I'm going to clear the figure. Okay. Clear all variables. Okay, and actually probably at the top I just should put in my name, and we can put in the date. Okay, I'm just going to call in the date, so read, just so that we have the information there. And so we're going to simulate a first order system. Okay, a divided by s plus b, where a is equal to 1, and b is equal to 5. Okay, so I'm just going to use these variables here. And so again, the first thing we're going to do is set a time step. So seems like a pretty straightforward system, so I'll just use my standard 10 millisecond, okay, time step, and then I'm going to create my time vector starting from 0 using my time step, and I'm not quite sure how long to run it, so I'm just going to start with 3 seconds and we'll see where we're at and make adjustments from there. And we need, remember, transfer functions basically state that the system is at 0. So I'm going to initialize my x equal to 0. And then I'm going to create my for loop. So for k equal to colon length of t, and then I'm going to evaluate my derivative. So we have, look on the other screen here, there's my equation, right? So dx dt. So I'm going to have x of k now, which will be the second one, is going to be equal to minus 5. It's this, right? Minus 5 times x of k minus 1 plus my forcing function. So I forgot to create my forcing function, so I'm going to come back up here. So you need to create your forcing function for all time. So I'm going to create my forcing function f, okay, is going to be all ones because it's a unit step, size of the t vector because it needs to match the size of the t vector. Okay, so this is going to be a unit step response. And so now then I can go to f of k minus 1, okay, and then I'm going to integrate using Euler's method. And so, I'm sorry, this was x dot. Sorry, that was x dot. That was the first derivative. Okay, and so now I'm going to integrate for x, which is equal to x, the previous value of x, plus the time step times x dot, the change at step k minus 1. All right, so we're going to end that, and then I'm going to go ahead and create my figure, and I'm going to create a subplot, and I'm going to plot my step response at the top. So this is going to be 2 rows, a top row and a bottom row, and I want the first row, and that's going to okay, so 1 column but 2 rows, and that's my subplot. And so now I'm going to plot t comma x, which is going to be my response. And if you want, you could also plot your forcing function if you want to see what that is like. Okay, and so we can create a legend. Step response. Forcing function, which is a step. Okay. And of course, you know, we have our y label is our amplitude. Okay, and I wasn't actually given units in this problem, so I'll just use the generic term units there. And then I'm going to create my subplot, and I just want to plot the velocity. Okay, and so we're going to subplot 2 comma 1 comma 2 to get the bottom row, and we're going to plot t comma x dot. Okay, now since I'm using x dot here, I need to make sure I initialize x dot also. Okay, so we need to make sure that we have a dot to match every t. So x dot was also equal to 0 because transfer functions are basically defined as being the all the initial conditions are 0. All right, so then I can Y label, create my Y label, and so this is going to be x dot units for that, and or actually probably units per second. So whatever the units are on the first one, this will be units per second, and then the X label is going to be time in seconds. Okay. And so I'm just going to go ahead and plot this for now. So I'm going to save this, and then I'm going to run it and look at the plot. Okay, so you can see that the step response is always 1. Okay, so I just plotted the step response there, and it's always 1. But notice the blue, which is, or the sorry, my forcing function is a unit step, so it's 1. But the actual response of the system is in blue, and it's only ending up at 0.2. So you see that it's ending up at 0.2. Now I ran this for 3 seconds, but if you look here, you can see that it actually pretty much reached the final value at about 1 second or 1.2 seconds. So I'm going to come back in here and change my file. So I'm going to come back up here, and I'm going to run this for like 1.2 seconds, because you want to make sure it pretty much reaches the final value. And it opened a brand new figure there. So I'm going to edit my script again, and I want to make sure that I'm going to figure 1. And because if you don't do that, it's wanting to open up a new figure every time. So I don't want lots of new figures. I just want the first figure. All right, so here's figure 1. All right, and so we can see that now. Really, since the final value is only going to 1.2, it doesn't really make sense to plot the forcing function on that same scale. Okay, so I'm going to go ahead and remove that forcing function. From the plot, but I just wanted you to see that that was there. Okay, and so now that's just how we simulate it. Okay, so again, we just took the transfer function, we cross multiplied here, and then solve for the derivative, right? And then we just evaluate the derivative and use Euler's then to integrate. Okay, so but when you evaluate the derivative, remember you have to add in your forcing function. And since we were simply doing a step response, our forcing function is just 1's the size of t. So that's our unit step response. And if you needed to scale that, okay, so really, I guess I typed in this. I should have actually used my variables I stated. So this would have been like A and B here. And then, of course, I would have to define those. Because up here, remember I said, well, this is like A divided by S plus B. And so, I need to actually define A and define B if I'm going to use that. B was 5. Okay. All right, so now we know, since this is a transfer function, we know that the final value is A divided by B. So I could actually, create a final value of A divided by B. Okay, so I know what this final value is. And then I could draw a line indicating that on my axis if I wanted to do that. So that we would have the plot. Okay, in this case, since it's a first order system, it's not going to have any overshoot. Okay, and so it's just going to be a nice, simple, slow response. Okay, but I can grab my axis values, right, using the axis function. Okay, and what I want to do is I want to set that second one equal to max time, because if you look at this plot, I don't know why figure 2 doesn't want to disappear. Drag it out of the way here. So when you look at this plot, right, you see that this plot is all going up to 1.4 seconds, but the actual simulation is only running to 1.2 seconds. So I want to make sure that it runs for 1.2 seconds. And so I'm going to set it to the max t, right, which is 1.2 seconds now. But the reason I'm using the max t is because if I want to change my time, it'll reset that. All right, and I know the max final value. I calculated that up here, right? The final value is A divided by B. And so I can say that the y max value, which is element 4 of this vector, okay, is the final value. However, I'm going to actually multiply it times 10%. So I'm going to multiply it times 1.1 and then reset my axes using this value. And then I'm going to turn my hold on, and I just want to plot a black dotted line. So I'm going to plot a horizontal line, which is going to be the final value. Okay, and I'm going to multiply it times a 1 by 1, because you need 2 points to plot a dotted line, right? And I'm just going to make this like a black dotted line and plot this just so that we can clearly see where that final value is. Okay, so I'm going to save this and rerun it. Okay, and I got a typo here. I've got an A. Must have used a lowercase a instead of upper A. Or oh, this was AX, my axis. Okay, that's what the A was complaining about. And we'll rerun that. And so here you can see, here's the plot. And by adding that extra 10%, it kind of gave a place for the legend. And you can see the dotted line right there at 0.2. So you can see that the final value is 0.2. You can see that's actually where it's ending up at, as we expected. Okay, so there is how we can plot first order transfer function using just the standard Euler simulation method, using a for loop and evaluating your derivative and then predicting your new value. Alright, so I just showed you how to do the simulation using standard Euler simulation of the transfer function 1 over s plus 5. Alright, but now what I want to do is show you another method. Alright, so both Octave and MATLAB have what they call a controls package. And so if you run package list in Octave, it'll list the packages you have installed, and you have to have the control package installed and loaded. Now, if you don't have this package, which you might not if you just downloaded it, you can go to the website, go to Octave. You can just put this into Google and search for it, but search for like Octave packages, and it'll take you to this website, and it shows you all the different packages that are available, and there's quite a few of them, and some of them are really cool. But what you want to do is just get to this page, and then you can find the control toolbox or control package. MATLAB calls them toolboxes. Octave just calls them packages. And you can just download this. And then once you have it downloaded, you can use the package command. Right? Remember, the help will give you help on it. You can run the package command. It's kind of running off the sides here, but if you run help package, okay, you can load the package, do a package install to install it, and then do a package load to load it. Okay, now it may have some other packages. If it gives you an error when you're trying to do the install, that's because maybe it needs some other package. So make sure you download that package and install it first if you get that error. I don't remember if it has any dependencies or not. Okay, but so once you've got that control package loaded and installed and loaded, right? And again, you can see that if you type package list, and you can see I have it. Number one, I have it installed. And then the star means that I actually have it loaded up. Okay, so that's what that star is telling me there. So once we have that, you can then create your numerator. So now remember that my transfer function is 1 over s plus 5, right? That s plus 5. That was my transfer function in the frequency domain, the setup of the transfer function. So what we need to do, well, let me just leave that there. Now it'll give an error when I hit enter, but I just want it to be on the screen. Okay, and so what we want to do is we want to define the numerator. So my numerator is just it's a polynomial of order 1. So you could since you have since I've got the s plus 5 down here, okay, the s would be your first one, so, but in the numerator I don't have an s, so I could just put a 0, or you could just ignore that and just put 1. You could do it either way, but I'll just show you that you can put that 0 in there. Then I'm going to create the denominator. Now the denominator, the s has a coefficient of 1, so I put a 1 there, and then with the s to the 0 term has coefficient of 5, so it's 1 comma 5, so that's my denominator. Now I'm going to create a transfer function, so I need a variable. I'll call this like just h of s, and I'm going to use the transfer function, which again is, see, the transfer function is built into this control package, or comes with this control package. That's why we need that. And then we can say num comma den, and we pass it the numerator, your numerator coefficients. You don't have to worry about the s's, you're just passing it the coefficients, and the denominator coefficients, right? So my denominator coefficients are 1, 5, and my numerator coefficients are 0, 1. And again, I could have just ignored leading zeros, it's no big deal. All right, but then I hit enter, and you can see it actually displays for me now. This is my transfer function. They throw in this y here, all right, but the variable name I gave it is h of s, and so it's 1 divided by s plus 5. That's my transfer function. So there it is, and they actually tell us that it's a continuous time model. And so now we're going to create our time step, right, is 0.01. Now I'm just doing this in the command line, but you really should put it into your M files, just like you would any other code. And then I'm going to create my time vector, 0, colon, time step, colon, and I'm going to run it for 1.2 seconds like I did the Euler simulation. And now I'm going to, now before, like, we had to create a step response, but there's actually a built-in to that control package, there's a step response. So what we can do is I'm going to just say like x or t comma x, and it'll return those vectors for me. And then I'm going to call the step function, and I'm going to pass it my transfer function and my time vector. All right, and so when I do this now, I'm going to leave off the semicolon, and you can see it's just dumping out the values. Okay, so if you put the semicolon, of course, it won't dump them out, but remember the whos command, we can see them there. Okay, and so I have my x value and my t value. Actually, I guess I never cleared it from before, so I have a bunch of other stuff in there too. But now I'm going to plot t comma x, and oops, hold on, I think I put them backwards. Read the help statement. Help step, okay? And so when you look at the outputs of the step, it's y and then t, so I had that backwards. All right, so let's recall that. Okay, so I should have had the output, which they call y, but I'm calling x, and then t is your time vector, which, I mean, I already have the time vector because I'm supplying it, but I'm just returning that back. Okay, and that may be messed up now. See, this is why we put this in an M file, because I think I just messed that up. Here's my figure. Come on, figure. Okay. So, yeah, I messed that up because I messed up my t vector on there because I had them backwards. So, all right, so that's going to say transfer using the control.m. So I'm going to put this like I should have done before and clear everything out, clear my figure, and then TS is equal to 0.1 and time is equal to 0 colon TS comma colon 1.2. Okay, num is equal to 1. Like I say, you don't have to put the leading 0 in there if you don't want to, because there was no s term in there. And then I'm going to have h of s is equal to transfer function num comma den, and then I'm going to have my step response now, and I'm going to have x comma t. So I'll put them in the correct order now that I read the help page, and run step and pass it my system, my transfer function, and I'm also going to pass it the time vector. Now you could leave the time vector off and it would return you a time vector, but when you do that, the problem with that is sometimes it doesn't run it long enough, or it runs it too long, and so I find I like to control T at the start, so I like to pass it my own T to use there, and then we can plot T comma X. Okay, and so then I'm going to run this. And we'll look at my figure and see now it looks better. And of course I can go back and do my labels and set my axes and clean it up a little bit. Okay, so but that is how you can use the control toolbox. Okay, so we can use this control toolbox in here, or or control package, okay, to do step responses used for transfer functions. So it's very, very, very easy to use. Again, all you have to do is set your numerator, set your denominator coefficients, and then call this TF function and pass it the numerator coefficient vector and the denominator coefficient vector, and it'll return that h of s, and then you can run the step response and plot it. Okay? So you don't have to worry about the for loop, because the package, the control package, is doing all the for loop and the evaluating of the derivative and evaluating Euler's, or they actually use a different method than Euler's, so it's a little more accurate when you use the control system design package here.